Okay, time to get started. So here's what we were talking about last time. We were talking about a new kind of line integral. Right, we've seen a bunch of new kinds of integrals in general in this class. We've seen, we started with single variable integrals, obviously. But double integrals is fundamentally different. Triple integrals are fundamentally different. Bunch of different techniques for how to compute those things. Not really new kinds of integrals, just new techniques for computing. But then we saw scalar line integrals, scalar surface integrals. Those really are different kinds of Riemann sums. Those are different sort of contexts for the chop it up, add it up strategy. So this is arguably number 6. Our sort of 6th kind of integral. The idea that with a curve in the plane or in space, when you chop it up, when you start writing down that which you will be adding up, it might be a dot product. Right? That depends not just on the size of the piece of curve, but also depends on the direction that the curve is pointing. Right? So this is a really different thing. So I'm going to call it a different kind of integral. So this is again routinely referred to as a line integral, which is the same word that we use to describe the other kind of line integral. And I guess that's fine, but I like to make a distinction, so I refer to the former, where you have a scalar integrand so these are vectors, but if instead of a vector, if this had been a scalar integrand like a density, and if instead of a vector as this is, if you had a scalar differential like a size, right, then we would call that a scalar line integral. These being a vector integrand and a vector differential, I call these vector line integrals, or sometimes line integral of a vector field. Okay, so we talked about that last time, saw some examples. Here's the formula for how to compute. Conveniently, we made this observation last time that the pullback, we've already got all the stuff set up that we need in doing the pullback. This vector differential dx, we already know it's VDT. Old news. We don't need to set up more machinery. Again, the sort of irony of sorts is that even though this is arguably a more sophisticated construction, it's a more sophisticated chop it up, add it up application, I guess you might say, it's really easier to compute them. Because you don't have to take square roots, right? Remember, if you're computing a scalar line integral, ds is magnitude of v times dt. So you have to take a magnitude of the velocity. Here, no magnitude. It's just a velocity vector. You do a dot product with it. Much easier. No square roots. Okay. All right. Examples. Okay. So we're going to show you a different notation for representing these things now. Here's our dx vector. We talked about the dx vector. It's our linear approximation to displacement along the curve. So it includes both a magnitude telling you an approximation of how long is that piece of curve, and a direction telling you approximately which way is that piece of curve oriented. Okay. And we know how to compute dx. It's v dt. Here's your v, right, times dt. That's all old news. The only observation I'm making here is that you can break that down into individual coordinates. So there is what I'm going to call an x-coordinate of that dx vector. So I'll call that the dx scalar, right? And then likewise, there is a second coordinate. There is a y-coordinate to that dx vector. And then there is a z-coordinate to that dx vector. You just look individually at its coordinates. And, in fact, you can just write down what they are. Again, we already know how to compute dx. Yeah.
Why is the little dz dt times dt, why is that important in computing the coordinate?
So we have this formula for, our old news formula is that dx is velocity times dt. Yeah. And this is velocity, and that's multiplying it by dt, just one coordinate at a time. Yeah. Okay, so we haven't done this before, looking individually at coordinates, but I mean, again, this old formula for dx, you can write down its coordinates individually as we have, and we could reasonably ask the question, what should we call this thing, this first coordinate of the dx vector? And gosh, it seems awful reasonable to call it dx doesn't it? I mean, think about what that first coordinate of the displacement differential is. That says how much does the x-coordinate change as you move along the curve from there to there, or more precisely, what is our linear approximation to how much the x-coordinate changes? Well, golly, if there were a thing that we'd want to call dx, I mean, that's it, right? How much did the x-coordinate change? Likewise, dy, how much did the y-coordinate change? Highly plausible, et cetera, et cetera. Okay. All right. So, now we're going to do some things with this. I am going to do a quick aside for a moment. This is foreshadowing for something that's going to come up in a week or two. So we're not going to do anything with the following thought for a couple of weeks, but it will be very important a couple of weeks from now. So anyway, bear with me on a little bit of foreshadowing. This dx thing that we have a formula for, and that we have a way of thinking of, how much did the x-coordinate change? What's our approximation to how the x-coordinate changed between those 2 points on the curve? What's a different way that you can think about it? So, other than how much did x change? So, here's the other point of view, and don't be asking yourself right now, why would I want to do this? I haven't given you enough information to make any expectation of why you'd want to do this, right? But just recognize for me that the following is equivalent. And it goes like this. Suppose you were to look at your piece of curve. Let's say this little piece of curve here, and let me zoom in so that I can see better. Take that little piece of curve. Suppose you were to project that piece of curve down to the x-axis. Right? Projecting that little piece of curve down to the x-axis, you would get a shadow, you might say, down here, of a certain size. I'm going to call that the absolute value of dx. Now notice that's true, right? Whether we are moving to the right, such as in this case, or whether we are moving to the left, such as in this case, right? In either case, the absolute value of what we already know as dx is the size of that projection. So we're not thinking of it as a change in coordinate. We're thinking of it as a size of a piece of the x-axis. Okay, all right. Now, but what about the direction? Sizes are absolute values. Don't tell us, well, was it going which way or was it going the other way? So the other thing that we're going to observe is we're going to observe that when you do this projection, the direction that the curve is going will either project the same direction that the x-axis is going, or the other possibility, the direction that the curve is going will project to a direction that is opposite of the direction the x-axis is going. So those are two possibilities, and so the innocent observation that I want to make, seemingly pointless, admittedly weird, right? But bear with me. Alternative point of view on what dx is dx is a thing, it's a number whose magnitude represents the size of the projection and whose sign represents forward or backward. That's, in fact, equivalent. Right? In other words, if you did not have a pre-existing notion for dx, and if you were to decide, I'm going to choose to think of dx this way, I'm going to write it down in these terms, you'd, in fact, be writing down the exact same thing. Okay, just wanted to plant that thought. Again, we're not going to go anywhere with that right this second. We're going to plant that thought and capitalize on it in a couple weeks. Okay, so where were we? We had written down this dx vector, and we had decided to give the following names to its coordinates. Yes?
How would we ever get the sign of dx given that it's just a variable?
Well, so no, forget about the computations. Right now I'm just thinking in terms of, look, I got a little piece of curve there, right? And that little piece of curve, we're assuming, by the way, that the piece of curve is going that direction. Right, and that little piece of curve I appeal to your geometric intuition. Forget about formulas, right? If I were to think about that piece of curve and if it were to just drop down to the x-axis, when it landed, it would be facing this way. That's all I'm saying. Yeah. Okay. All right. So we've got our dx vector. Thinking of it in coordinates. And now here's the innocent observation that I'm going to make. Remember our formula for a vector line integral was this. And then, don't forget, we've got a convention that when we write a vector field, very often we'll write its coordinates as PQR, arbitrary, whatever. So there's the vector field written out in coordinates. And now, per the observation on the previous page, we can write the dx vector in coordinates. Check it out. We're doing a dot product of things where we can now see the coordinates. So we can crank out this dot product explicitly. Cranking out that dot product, the green vector field coordinates, the yellow differential coordinates, just dotting that out like dot products do. And you get this expression here. So this is an alternative notation for vector line integrals. And you're going to see these. They're out there. You're going to see this as a way of writing down this vector line integral that we know we have applications for. That helps us compute work that it takes to travel through a force field, or it could represent something about fluid flows, and that's a highly natural and physically relevant thing. And here's an alternative way to write it down. Right now, new awkwardness. We have here a brand new kind of integral. This is an integral that we're not going to motivate physically. All of our previous integrals we've motivated physically. How am I going to compute the mass of this thing? How am I going to compute how many ants are crawling over that thing? There's been some sort of a real world application to motivate. This is just notationally, I need to write this down, and so let me write down a definition. And so here's our definition, just in order for this expression to make sense. There's arguably nothing new here. I'm still using dx as dx dt, just like I did on the previous page, just now sort of individually instead of as a coordinate of a vector. So, anyway, here it is. Now, looming question. Why in the world would I want to do this, right? Why would I take a perfectly relatable notation like this one, highly relatable, right? So force, displacement, I can see what's in that formula, I can see where they come from, I can see why I'd want to do a chop it up, add it up, that's highly natural. Why would I want to take that natural notation and rewrite it as this? This new notation we have is longer, clunkier. I don't yet have any geometric intuition or physical intuition about how I should think about one of these expressions by itself. Where are we going with this? Right? Very reasonable question. And I'm not going to be able to give you a particularly satisfying answer to that question, unfortunately. So here's the deal. There's two reasons that you need to know this notation. One is, as a kind of a cultural point, you should know there are great and powerful things that you can do with this notation in more advanced context than Math 212. So this is not a bad choice. In general, this is an excellent choice. In general, for reasons that I can't tell you. The other reason you need to know is that this notation is used a lot, even when there's no particular reason to. So there are plenty of situations where you're going to see, instead of that, you're going to see someone write down that, and you just need to be able to recognize it. I mean, you're going to be doing multivariable calculus here for some reason, I assume, right? So in your professional futures, in your academic futures, you're going to see vector line integrals written down, and sometimes they're going to be written down like this. And so I need you to know what to do with them. When you see something that looks like this, you need to realize, oh, okay, these things here make up the vector field that this is a vector line integral of. And these things here are just how they're writing it sort of one coordinate at a time, the dx vector. So just heads up, when you see something like this, recognize that it's an alternative notation for this. Okay. All right, and that's pretty unsatisfying. And that's kind of the way it has to be. We just can't go, Math 212 is not, we don't have the background or the time, frankly, to go into how useful this can be. Okay, so summary of notations that we've seen. All of the notations that are on this page represent the exact same thing. Notice I've got equal signs here. All of these are the same thing. Alternative notations with their various pros and cons. This was the first one we wrote down. This is a formula we wrote down to help us compute it. After all, that is a pullback. That's a single variable integral. That's nice. These notations we wrote down when we were trying to figure out how to make sense out of what this, how to think about this in the point of view, in the context of fluid flows. Right? So these are nice points of view in those contexts. And then here's this, historically relevant, sophisticated notation that we're frankly not going to do much with in this course. Okay, so be aware of the various pros and cons. You can, I suppose, technically write any of these down. I will reveal I have a personal favorite. That's my personal favorite of these notations for a couple of reasons. One of which, born of sheer laziness, that one requires the fewest pencil strokes. That's got an appeal, right? That's nice. Right. But here's the other reason. I think, and this is, I think, really nice. This notation here is extremely elegant. It's very natural. As follows. Keep in mind we're representing a chop it up, add it up. Right? During which we chop up pieces of that curve, C, the domain. What's nice about this notation is written as a single item over here on the right of the dot product. That dx differential tells you exactly everything you need to know about the little pieces of curve that you chop it up into. So there's a really nice distinction here. We have over here that which is clearly integrand, and we have over here that which is clearly differential relating to the domain. And seeing those separated like that, I think is really nice. Note that that's not really the case. For example, with this notation here, it looks like that's all integrand. But it kind of isn't, because this t vector is really something that comes from the curve itself. It's arguably really part of the differential that's telling you about pieces of the domain. So that notation is, in this sense, a little inelegant, just in my opinion, and a little clunky, in a way that this is very nice. Okay. Anyway, whatever that's worth. So you're going to see on my tests this notation a lot because I like it. Right? That said, on other, in other contexts, maybe on the final, keep in mind, I don't write the final exam. The final exam is a joint written thing between all the instructors, right? So I can't control completely how you're going to see things. You very well might see this notation on the final exam, and just make sure to realize it's the same thing. Alternative notation. Likewise, you might see this or something along these lines. Again, heads up, make sure to know what it is. It's the exact same thing. Alrighty. Okay, so new topic. We'll talk about a new thing called the fundamental theorem of line integrals, which is a lot like the fundamental theorem of calculus, not just in the name. Fundamental theorem of. So the fundamental theorem of line integrals is a very powerful result. Amazing things can be done with it. It's also the first example that we're going to see of a long line of theorems, powerful theorems, sophisticated theorems that make up why Chapter 15 is so important and so interesting and challenging. Okay, so this is the first step in an important direction. Couple things I'm going to say about it. First of all, we're going to consider the simplest possible case here. Things get weird and complicated in deep ways when we have differentiability problems, regularity problems. So I'm going to assume, for the purposes of this discussion, that everything is continuous, everything is differentiable everywhere. Underscore everywhere. If there is so much as a single point in the domain where the integrand is, or where the where some function or vector field or whatever is undefined or not continuous, very bad things can happen, right? So we're going to assume everything in sight is universally differentiable and nice. Okay. All right. Second thing I'm going to tell you about the fundamental theorem line integrals before we actually get to it is it is highly analogous. I guess I already said that to the fundamental theorem of calculus. So in order to have a good segue, a good sort of entry into the fundamental theorem of line integrals, I want to go back and talk about the fundamental theorem of calculus a little bit. And I know y'all already know the fundamental theorem of calculus. Correction. You should all know the fundamental theorem of calculus, but I guess I have to recognize some of you who came into this class from AP Credit may know how to compute integrals really well, but not technically know exactly what part of that process actually is the fundamental theorem of calculus. So anyway, if you're not 100% clear on that point, definitely want to clear that up as soon as possible. Come to my office hours. I'll be happy to give you a discussion about that. Okay. So I'm going to give you a new point of view on the fundamental theorem of calculus. Point could be made that you already know how to use the fundamental theorem of calculus. You may even know how to prove the fundamental theorem of calculus. And that's all good, right? I'm going to show you a different point of view on the fundamental theorem of calculus that you may or may not have seen before. The point to this is not to solidify your fundamental theorem of calculus knowledge. The point to this is to take a perspective on the fundamental theorem of calculus that will generalize very nicely to help us understanding the line integral theorem. Right? So this is setting a stage, not just the calculus theorem itself, but the point of view specifically that we're taking here is playing a role to set a stage for us. So again, even if you're quite confident in your knowledge of the fundamental theorem, bear with me. Okay. I'm going to start off with this seemingly wrong question. How would I compute f of b minus f of a? That seems silly. Isn't that supposed to be the answer, not the question? Right? Most people think of the fundamental theorem of calculus as, hey, I've got this integral. I didn't even know how to compute this integral. How do I compute this integral? Oh, fantastic. I can use this formula. Right? So this is very often thought of as the answer to the question. I want to view this as the question. Okay. So, weird, I confess. Bear with me. Okay. So the first thing I want to observe about this expression is that this expression here thought of as how much does f change, right? I mean, that's what f of b minus f of a, that says how much does f change between the point A and the point B. That is an accumulating quantity. This is going to be a really important concept for us in Chapter 15, the idea of an accumulating quantity. So let me talk about what I mean by an accumulating quantity. Mass is an accumulating quantity. What I mean by that is, suppose I take a region of space that has some mass in it. If I were to take that region of space, this solid, right? If I were to chop it in half, and if I were to ask, let's look at the mass over here, let's look at the mass over here, the mass in the original region is the sum of the masses in the two individual regions that I got when I chopped it. Okay? So that's how mass works. You might call that conservation of mass or something. I call it the accumulation feature of mass. Now you might say, well, duh. Right? Well, of course. What could possibly, this is the most obvious thing in the world. Let me point out, not everything you might want to compute necessarily has this feature. This is a special feature that mass, as a concept, has. Here's one that doesn't. The surface area of a solid does not have this feature. If you take a solid three-dimensional region, and we can talk about, but on the outside there is a surface area there, and how much surface area is there? The surface area of the solid is not the same as, if you were to chop it and separate it into two separate chunks, the surface area of this plus the surface area of that is not the same as the surface area of the original. Because when you chop, you make new surface. Right? So, doesn't have this feature of accumulation that, when you chop it up, add it up, that the quantity is preserved. So anyway, this is, I think, a nice feature. Mass has this feature. Ants population have this feature, right? Change has this feature of accumulation. So specifically then, if you look at interval here from A to B, and if you were to cut it somewhere, I don't know, let's say there, right? If you're interested in how much the function changes between A and B, that is the sum of how much did it change between A and C, plus how much did it change between C and B. Change just has this feature. That's how change works. Right? Silly example I like to think of is think about your height as you've grown up since you were, let's say, since age, I don't know, approximately 18, I guess. Since you were 8, from ages 8 to 18, your height has done kind of like this, right? There's been a change in your height over time. Well, their total change in height that you've experienced is the sum of how much height did you gain in the first year? How much height did you gain in the second year? How much height did you gain in the third year? Right? The total of the individual changes adds up to the grand total change. Okay. So anyway, this isn't it. Like I say, it's an important feature for a question to have. This thing that we're looking at, change, has this feature of accumulation, and I'm going to mathematically write that like this. All right. This expression is true no matter how many slices you take. This is not an approximation. That's exactly. Right? Change is not approximated by a sum of individual changes. Total change is exactly the sum of individual changes. So it doesn't matter how you slice. I could even say, suppose I slice finer and finer and finer and finer. It doesn't matter. You're taking a limit of something which is a constant. It's always the same. Right? So I can put that limit in there for free. Okay. I'm going to multiply and divide by delta x. That's legal. Right. Multiply and divide by the same thing. Nothing really happens. And what I get then, thinking of delta f as this expression, is a way of thinking that, okay, well, how much change there is in a given little delta x interval relates to the size of the interval as follows. The size of the interval, you multiply by this thing here, whatever that is, to get you the actual change. Okay. Why would I want to do that? You might be seeing this coming at this point, but note I have a limit of a sum of a thing times delta x. Where have I seen that before? That's a Riemann sum. Right? And being as it is a Riemann sum, that is an integral. Right? And in the limit, we know what that expression turns into. That expression turns into the derivative. Everybody on board? Okay. All right. So, so the idea then is we think of the left-hand side of the fundamental theorem of calculus as representing an accumulating quantity, that being change. We represent that summation. We represent that accumulation with a summation. play a couple little games, and then rewrite it as an integral. Okay. All right. So now there's your familiar result. This is the fundamental theorem of calculus. Again, we normally think of it as going this way. We think of it as, we've got an integral. How do I compute it? Formula, f of b minus f of a. I am thinking of it the other way. Doesn't matter. Equal signs go both ways, right? So suit yourself. I'm choosing to think of it this way. It's going to end up being much more convenient as we try to extend the analogy here. Okay. Okay, one other thing I want to mention, just to kind of get a little bit of foreshadowing. I want to lay some groundwork for something that's going to be convenient later on. We have seen before an accumulating quantity computed with an integral. And I just want to make this observation. We have seen this before, and we've seen many examples before. One of them I've already mentioned was mass. So let me write down how that works. Mass is an accumulating quantity, right? Change accumulates, mass accumulates. How do we compute mass? Well, it's an integral from a to b dx, just like that is. And it is an integral specifically then of this function, delta of x, which of course we know as mass density. Okay. Remember, we interpret the word density in broader terms now. Forget ninth grade physical science class, where density was always strictly, mass per unit volume. That was the rule, mass per unit volume. Now, density means stuff. I don't know. Maybe it's mass. Maybe it's population. Maybe it's who knows what. Stuff per unit size. Right? Okay, so here's the thing. We've got these two calculations. These are highly parallel calculations. On the one hand, mass is an accumulating quantity that's computed as an integral of mass density. Well, by analogy then, I would like to think of this calculation up here as being a computation of change, thought of as an accumulating quantity, and it is likewise a computation of an integral of its associated density. I would like to call that change density. Totally by analogy with the fact that here we call this mass density. In both cases, we're doing an accumulation. In both cases, it's this accumulating quantity. It's adding up over the interval from A to B. Something is being multiplied by size. Accumulating quantity per unit size. I mean, they're really analogous calculations. It's just a different accumulating quantity. So, change density. Now, I bet you strong odds you've never thought of derivatives as a density before. This is definitely a new way to think about derivatives. You've in the past thought of derivatives as slopes of tangent lines. Yeah, right. You've thought of derivatives as speeds, velocities, that kind of thing. That's a nice application as well. Different points of view that are useful in different contexts. You might have even thought of derivatives in terms of what I hear economists describe as sensitivities. So, if you have some parameter of an economic system, and if you change that input parameter to the system, then the output parameter in the system is going to change by a certain amount. And the relationship between that input change and that output change, how sensitive is this output to changes in this input, right? So that's another way to think about a derivative, sensitivity. So sensitivity, velocity, slopes. Never seen the density point of view before. It's a new perspective, granted, right? Don't make the mistake of thinking, I have enough perspectives already on the derivative. That's a mistake. This is a very valuable point of view, and this point of view on the derivative is going to be very handy as we move on through chapter 15. So I want to, even though the derivative, I roll, oh my gosh, that's Calc 1, that was like a year ago, right? It's so long, oh my gosh, I was in high school when I learned about the derivative. Are we really going to rehash all of that stuff? Yes, this is a point of view that never gets said in high school classes. Very valuable. in what we're about to do. So try to absorb that idea. Try to think of the derivative along the lines of mass density as stuff per unit size in that sense. Okay. Okie dokie. So let's see if we can steal the ideas that we just talked through and apply them in a different context. Quick reminder, what was our idea? Our idea was up here that we were going to think of change. We were going to notice that it accumulates. We were going to try to turn that into something that looks like an integral, and then hope that we can make the details work out. So here's another context that we reasonably might want to deal with. Suppose, forget about single variable calculus now. Suppose I have a curve in R2 or R3. Let's think of it in space, because why not? Curve in R3. And suppose that it's got a starting point A, and it's got an ending point B. And suppose I want to compute f of b minus f of a. Same concept, really. I would still want to compute change. Now, instead of this being, just how to, a single variable changing, the x-axis, something like that. Here, maybe we're driving along a road, and I want to know how much does altitude change from where I started driving to when I ended driving. Or how much did temperature change from when I started to when I ended, or barometric pressure, or whatever. It is still an accumulating quantity. That is still change. Change still accumulates. That is, the total amount of change is, how much did f change on that first little piece, plus how much did f change on that second little piece, plus how much did f change on that third little piece? If you add up individual changes, you get total change. Right? That's how change works. Think about the altitude example. If you want to measure the total difference in altitude between the point A and the point B, you could, if you had a lot of time and a really good instrument for measuring level and such, right? You could take a carpenter's level and just, each, 6 inches or foot or whatever along the road, see how much altitude you gained each little step along the road. And you add up all those little changes in altitude and add them up, you get the total change in altitude. Everybody on board? That's kind of like what we did with the fundamental theorem. It's a very different context. Now we're accumulating over a curve instead of accumulating over an interval. But it's morally the same idea. But by the way, just like mass, right? In Calc 1 classes, you talk about how to compute the mass of a single, straight line rod on the x-axis. And then earlier in this class, we talked about, but what if that rod is all bent and curved around and stuff? You still chop it up, add it up. Okay, all right. Okay, change accumulates. This is still totally independent of how many slices you take. This is always exactly that same expression. It's independent of the slicing. So you can take a limit for free. It doesn't matter how many slices you take or if the number of slices you take approaches infinity. Knock yourself out. You're still going to get the same total. The limit of a constant is that constant. Okay. Now here's a chapter 13 reference. How do you compute a change along a piece of curve? Well, along a piece of curve, you estimate the change in the input by delta x. We've got this, I should call that dx. We've got our displacement differential, right? And the change in the output relates to the change in the input, right? Input changes relate to output changes by way of the multivariable derivative, dot product with the gradient in this case. Anyway, reminder, this is a flashback to an old formula for chapter 13. Input changes relate to output changes by way of dot product with the gradient. Everybody remember that one, I hope. If you're a little rusty, by the way, highly possible if you're a little rusty on your chapter 13, go back and brush it up, right? And go through the recordings and, maybe listen to some of those recordings again. Okay, and again, we find ourselves in this situation. This is something we've seen before. We're taking a limit summation along a curve that involves a dot product with our position differential. That's exactly a vector line integral, like we defined last time. Specifically, it's a vector line integral of the gradient field. Remember, we talked about this is the sort of resolving of a bit of foreshadowing we did when we first introduced vector fields. And remember, I made the observation that gradient fields, there's something very special about gradient fields. This is one of the things that makes gradient fields special. Interpreting the gradient not as just a single vector, but interpreting it as a vector field in the entire domain of the function. This is one of the nice applications. And by the way, there are more. Okay. All right. So we have ourselves a brand new theorem. We've derived here a kind of I don't want to say generalization, but we've adapted the fundamental theorem of calculus, right, to a new context. This is what you might call the fundamental theorem of calculus as it applies to line integrals of vector fields over curves in space instead of, intervals. Right, like you see in a Calc 1 class. Right, so that's kind of a big deal. Thus the name, fundamental theorem of line integrals. Everybody on board? Highly plausible? Very strong analogy between how we derived this and how we derived the fundamental theorem of calculus on the previous page. All right. Okay. Now the first thing that we did over here with our fundamental theorem of calculus was make this interpretation. Oh, I didn't want to erase all that. Whoops. Make all this interpretation of how you can think of. Get that. There we go. You can think of the fundamental theorem of calculus as a motivation for thinking of that as a density, sort of by analogy to this being its analogous density. So, is there something like that going on here? And the answer is kind of, in a way that I can't really fully elaborate on right now, but we'll come back to at a later date. But in a way, this is a kind of like a density. Just not 100%. Here's the problem. If I want to think of this as a density, I have to come to terms with the fact that it's a vector. We've never seen a vector be a density before. Here, in this case, it's actually kind of more convenient to think of this dot product right in this way. Remember, we have this whole idea of dx is TDS. Right? Remember that one from the fluids point of view, vector line integrals. And from this point of view, notice that thing really does play the role of density. That is explicitly change per unit size. ds represents the size, the length of a little piece of curve that is your domain, right? So is the gradient density? Not quite. The gradient is something that you can use to compute density. You have to then dot it with the direction vector of the curve. So it's a change density after a fashion, but it's a change density which also has a direction, where that direction is telling you sort of more information in some sense. Namely, what is the direction the change is actually happening. So I like to call the gradient an oriented change density. It's just almost telling you change density, but with this additional aspect that has to be dotted out by the t vector. So anyway, I'm going to use this term oriented change density later on. This again is just a little bit of foreshadowing, but I did want to close the loop on the pattern that we were extending to the fundamental theorem of calculus. That yes, there is kind of a density point of view here. We'll come back to this later. Okay. All right. So we got a new theorem. How do you use the fundamental theorem of calculus? Well, if your integrand is a derivative And if you can find that antiderivative, then you're good, right? That's how we use this theorem right here. If your integrand is a derivative, see it says so right there, derivative. If your integrand is a derivative, and if you can figure out this antiderivative, then you've got a powerful tool for computing integrals. Good news. Every continuous function is a derivative of something. That's a neat consequence of the second version of the fundamental theorem of calculus. Flashback to Calc 1. So in single variable calculus, what it really boils down to, I mean, you don't have to worry about whether something is a derivative. Everything's a derivative as long as it's continuous. In the fundamental theorem of calculus, finding the antiderivative is really kind of, that's the meat of the matter. And y'all remember those days, right? Of the oh my gosh, how do I integrate this? How do I integrate that? How do I find this antiderivative? How do I find that There was a lot of anti-differentiation techniques. You know, the integration by parts and substitutions and partial fractions and oh my gosh, long list of techniques. Yeah. Oh, okay. Yeah. So you would think there'd be an analogy there, and there kind of is. If you want to use the fundamental theorem of line integrals, well, here it is, fundamental theorem of line integrals. If your integrand is a gradient, and if you can find this function, the thing whose gradient is your integrand, how would we say that? The thing that, the gradient of f is my vector field, So what is it that I do to the vector field to get f? I like the term anti-gradient, right? Highly analogous to antiderivative. I like to think of f as the anti-gradient. So if your integrand is a gradient, and if you can find your anti-gradient, then again, hey, you're off to the races. You've got a tool for computing integrals. Here's where the analogy breaks down. This is not a given. It really isn't, and this is not a regularity problem. It's not sometimes things have discontinuities. There are harmless-looking, perfectly smooth, infinitely differentiable, world's most unthreatening vector fields that have no anti-gradient. That's a big problem. That's going to be a real thorn in our side throughout chapter 15. Unfortunately. So anyway, heads up for that. Don't just assume this anti-gradient exists. Sometimes it does not exist. It's not that we don't know how to find it. It's not that we don't have the techniques. It does not exist. So, sorry. But anyway, often it does. Sometimes it really does. And if you do have an anti-gradient, and if you can find that anti-gradient, then off you go. So here's an example. Now let's look at this. Here's a line integral that I want to compute. Here's a vector field f given. The domain here, C, is not only given, but it's parameterized. Right? So I've got an integrand. I've got a curve. Compute the line integral. Maybe we're computing work here. You know, how much work does it take to move along this curve while applying forces given by f, right? So how would you do this? You, of course, could plug and chug. You've got a parameterization given to you, and you could, cram it all in there and do a pullback, and that's fine, I guess. Hey, let me show you why I don't like the pullback strategy here. It would get super ugly. Look at these functions. Your x, y, and z, right? So that y that you see right there, that's sine of pi t squared. This z that you see here, that's t cubed. When you do the pullback, don't forget the pullback, f dot x prime dt. Well, you're going to have to then take the derivative of this ugly curve. It's going to have a super ugly velocity vector. And that's going to figure prominently in your calculation, doing the pullback. Right? So doing a pullback here would, highly undesirable. Right? I mean, by the way, it would work. I mean, if you can crank through it, it would work. But let's see if we can find a better way to do this, a much more desirable way to do this. and turns out the fundamental theorem of line integrals is exactly the choice. That vector field, I notice, is a gradient. Hey, look at that. It's exactly the gradient of this function here, x plus yz. And x partial gives you that, y partial gives you that, z partial gives you that. This given vector field is a gradient, and I have found the anti-gradient. So we're off to the races. We can plug into our brand new theorem here. We have found this anti-gradient, and so I can compute the integral by just this convenient formula, f of b minus f of a. Everybody on board? And it's all plug and chug for the pretty much the rest of this example. I'll let y'all read through the rest of this example. You just plug in the endpoints. So this curve starts where t is equal to 0. You got to plug in and see where that is. It's e comma 0 comma 0. I guess I'm going to do this after all. It ends when t is equal to 1. Plug that in. Little bit of arithmetic there, but e squared comma 0 comma 1. Those are your points. You plug those into your anti-gradient. F. And the integral is f of b minus f of a, which is compute e squared minus e in this case. And notice how painless that was. I didn't have to find an antiderivative. I didn't have to multiply all that out, all this ugliness in here. I didn't have to deal with it at all. Fundamental theorem of line integrals spared us all of that effort. It was really nice. Okay, very quick comment before I let you go. I did pull a rabbit out of a hat here. I just conjured, right, out of thin air with no evidence of where I got it from. I conjured this anti-gradient. That was a nice trick. How are you going to do that? Right? It's relevant. You can't just conjure anti-gradients. There is a technique for how to find anti-gradients, and that's what we'll talk about next time. See y'all later. Have a good one. Oh, and I do have homeworks to return if you'll stick around for a moment. Also, if you came in after I checked attendance, make sure that I get you